Hello everyone. This talk involves lithography-free fabrication of Coaxial gallium arsenide nanowire tunnel diodes. For a few reasons, this talk should be interesting for you. In general, Coaxial nanowires have a potential application in many devices. One of them is solar cells, and in particular, this work presents a novel nanowire growth method that combines metal-organic chemical vapor deposition and atomic layer deposition, and potentially can lower the cost of device fabrication for the large area of differs. And when we talk about the future generation of nanowire solar cells, if we want to compete with the current technology of multi-junction solar cells, we have to move from one cell nanowire to multi-junction cell nanowire solar cells. The current technology uses several PN junctions stacked on top of each other, and they are connected via tunnel diode devices. If you want to fabricate the future generation of Coaxial devices, you should have multiple PN junctions stacked on a core, and we need the nanowire tunnel devices to connect the shells together. So this work starts off with the fabrication of core gallium arsenide nanowire, and then we take advantage of gallium trioxide to basically isolate the substrate from whatever material deposition that can occur on the substrate, and we can proceed forward with the P-type and Coaxial fabrication of the nanowire. So we start with the gold-catalyzed gallium arsenide nanowire growth. We use metal-organic vapor phase epitaxy. A thin film of gold is deposited on the gallium arsenide substrate, and upon annealing, the gold nanoparticle is formed, and with introducing the gallium and arsenic precursors, the nanowire will grow through the VLS process. It is the same picture of an array of gallium arsenide nanowires. We can control the doping, N-type doping with tellurium, and P-type doping with introducing zinc sources. The next step is we use atomic layer deposition to deposit gallium trioxide all over the vapor with the grown nanowires. Here is the schematic of the final device after deposition. It's a 10 nanometer film of gallium trioxide covers the substrate and also all over the nanowires and gold particle. Here is the transmission electron microscope of the nanowire. You can see a conformal layer of oxide covered the entire surface. And the next step is very interesting. Upon annealing the nanowire in the MOCVD reactor at an elevated temperature, the gold dissolves gallium oxide, and basically this oxide on the surface will be removed. You will have a fresh gold catalyst on the top of the nanowire. And as soon as you introduce the precursors, you can regrow the nanowires. At the end, the device looks like the nanowire is sticking out of oxide and connected to gallium arsenide substrate. Here is the same image of the N-type gallium arsenide devices. The bottom is you can see the image contrast. The bottom one is the Coaxial gallium oxide gallium arsenide, and the upper part is the regrown gallium arsenide nanowire. Here is the TM image of the device. In the lower part, you can see it's covered with the gallium trioxide, and the rest is the high quality crystalline gallium arsenide, and no trace of oxygen whatsoever was seen on the nanowires. It's important to see how good these wires are in terms of electrical conduction. We use the nano-probing technique. It's the metal nano-probe inside a scanning electron microscope. It contacts the tip of the wire and applies the bias voltage to measure the current running through the wire. After analyzing devices, you expect to see Schottky behavior due to the presence of metal-semiconductor junction here. Here is the current voltage graph of a few devices for different diameter nanowires. You see a current rectification as it's right from the Schottky junction, and it can be analyzed as we go on Schottky equation. We get very nice diode quality, close to 1 ideal factor, and the doping of the wire can be controlled and extracted from the fitting to the data. We have mid-10 to 17 for these gallium arsenide nanowires. The next one is making ohmic contact. If you want to make tunnel layer, you have to have ohmic contact with the devices. To do so, we lowered the Schottky junction, the Schottky barrier between metal and semiconductor by using the degenerately doped shell of gallium arsenide. Here is a schematic of the device, undoped core, and a thin shell of highly doped 10 to 20 gallium arsenide p-type, and it makes a very nice ohmic contact with the layers. This is the current density given for the various diameters of the devices. After that, having resolved the ohmic contact issue and the outside control on the substrate, here is the structure of the final device. So at the very bottom you have the gallium arsenide substrate, it's M+. On the substrate is covered with gallium trioxide. This basically isolates and saves the substrate from whatever deposition that can occur on the surface of the substrate. This oxide is really important. And at the rest you have the PN Coaxial junction. And we control the doping level for the this coaxial tunnel diode here. The N-type core was set to mid-10 to 18, and shell to a degenerate segment of 10 to 19, mid-10 to 19. An intrinsic layer was placed here to stop any axial conduction from the top, from the goal, and the ohmic contact was made to the goal using the degenerate p-type segment. So basically, if you measure this tunnel device, the current flows from the goal, goes to the shell, and from the shell to the core. You have radial conduction of this device. Here is the TM image of a nominal device. Here the segments are marked. And when you analyze the electrical properties of devices, you see a typical tunnel behavior as you expect. You get reverse current, you get ohmic current at reverse bias, and you get a maximum current and the drop, and then the thermal diffusion current. This is given for a few diameter of devices. I replot the forward bias for you in the similar plot. These devices were grown with a 35 nanometer degenerate gallium arsenide shell, and this is how the forward bias current look like. The first region here, you get the tunnel current. You have the maximum current, and then the current decreases as you apply higher bias to the band structure of PN junction and cross, and basically the current decreases, and after that you have the regular thermal diffusion current, and you see the current rectification, but usually the PN junction, it's this part. So the first part of the curve is given by the tunnel current, characterized by peak voltage and current voltage, and the second part of the graph is the well-known PN junction current. We've made a very nice peak-to-valley ratio of 3, peak current to the valley is 3, and the peak current density is 20 to 52 amps per centimeter square, which is comparable to the planar tunnel diodes used in multi-junction solar cells. This is very promising. And at the end, so we had a very good control of doping of the Coaxial devices. The managed to combine MOCVD and ALD to cut down the cost of the device fabrication. Eventually, for larger devices, and we fabricated the state-of-the-art structured gallium arsenide nanowire tunnel diodes. And thank you for your attention.